Hey there. Welcome to AB Engineering Guild, your hub for real-world engineering, simplified. In today's video, we're breaking down open channel flow, what it is, how it works, and why it matters in fields like agriculture, flood control, and irrigation. If you're into engineering made easy, you're in the right place. Let's get started. Here are the contents that we will be discussing today. Introduction. Open channel flow is a type of fluid movement where the water flows with a free surface open to the atmosphere. This is different from flow in closed conduits like water pipes, where the flow is under pressure. Open channel flow is driven primarily by gravity, and the shape and slope of the channel greatly influence the flow characteristics. It occurs naturally in rivers and streams and is also commonly engineered in irrigation canals, drainage ditches, and floodways. Studying open channel flow is crucial in fields such as agricultural engineering, civil engineering, and environmental management. It plays a vital role in designing efficient irrigation systems, managing stormwater and flood control, ensuring proper drainage, and maintaining healthy natural waterways. By understanding the behavior of water in open channels, engineers and planners can develop solutions that conserve water, prevent erosion, and protect infrastructure and ecosystems. In simpler terms, open channel flow refers to the movement of liquid, usually water, where the surface is open to the atmosphere. Unlike water in pipes, this flow isn't pressurized. Instead, it's driven by gravity and shaped by the channel it flows through. You see open channel flow in everyday places like rivers, streams, irrigation canals, drainage ditches, and even flood channels. These systems are shaped by natural and man-made designs. Key factors like the slope of the land, the shape of the channel, and surface roughness all influence how water flows. Understanding these characteristics is crucial for engineers who design systems for irrigation, flood management, and proper drainage. In short, open channel flow is everywhere, and mastering it helps us manage water wisely and sustainably. Now that we already know what is an open channel, let us discuss the role of agricultural and biosystems engineers in open channel flow. Agricultural and biosystems engineers play a vital role in the development, management, and sustainability of open channel systems, especially in rural and agricultural areas. 1. Channel design and layout. ABES are responsible for designing open channels like irrigation canals and drainage ditches. For example, in rice farming areas in Nueva Ecija, engineers lay out field channels that ensure water is distributed evenly across the paddies with minimal loss. They consider slope, soil type, and water demand to optimize flow. 2. Hydraulic analysis. They use equations like Manning's and the continuity equation to analyze flow velocity, depth, and discharge. This ensures channels are neither too deep nor too shallow, which can affect efficiency. For instance, they simulate how floodwater might flow through a drainage canal in a banana plantation to prevent waterlogging. 3. Construction supervision. Once a channel is designed, ABES supervise its construction. They make sure the canal's slope, lining, and width follow the plan. For example, when a diversion canal is built in an upland vegetable farm, the engineer ensures it can handle the maximum flow during the rainy season without breaching. 4. Flow monitoring and control. ABES install and maintain devices such as partial flumes and V-notch weirs to measure the flow rate accurately. In irrigation systems like those in the National Irrigation Administration (NIA) projects, these tools help monitor water delivered to various farms, ensuring fair distribution. 5. Soil and water conservation. Open channels often pass through agricultural lands prone to erosion. ABES design silt traps, check dams, or line channels to prevent soil loss. In corn farms in Bukidnon, they may line the channels with concrete to avoid scouring during high flow. 6. Flood and drainage management. To prevent flooding in low-lying areas, ABES design stormwater drainage systems and retention ponds. In urbanizing areas with farms nearby, like parts of Laguna, engineers build integrated flood control systems that connect drainage canals to lakes or rivers. 7. Environmental protection. They also ensure channels don't harm nearby ecosystems. In fishpond areas of Pangasinan, for instance, they design overflow channels to avoid polluting nearby mangroves or estuaries. ABES help balance productivity and environmental care. 8. Policy and planning support. Finally, ABES help create local water use and flood management plans. They provide technical advice to LGUs and DA offices when drafting policies on irrigation schedules, disaster response, or watershed protection. Let's now move on to the different types of open channel. There are two main types of open channels, natural and artificial. Natural channels, like rivers and streams, are formed naturally over time. They often have winding paths, uneven bottoms, and irregular sides because nature shapes them freely. Examples are rivers, creeks, and streams. In contrast, artificial channels are built by people for specific purposes, such as bringing water to farms or draining rainwater from roads. These channels are usually straight, smooth, and more controlled in shape. Understanding the difference helps us know how water behaves in each type of channel and how we can design systems to manage water effectively. Examples are stormwater drains, irrigation canals, drainage ditches. To enlighten your minds about the said examples, here are the images that depicts natural and artificial channels. Next, we go to the types of flow in open channels. When studying open channel flow, it's important to understand that water behaves differently depending on several conditions. These behaviors are grouped into different types of flow. First, we have steady and unsteady flow. In steady flow, the depth and velocity of water remain constant over time. Picture a gently flowing irrigation canal on a sunny day. It delivers water smoothly and predictably to farms, making water management easier and more efficient. In contrast, unsteady flow occurs when water conditions change with time. This can happen during a sudden release from a dam or flash floods after a storm. Monitoring and predicting unsteady flow is crucial for early warning systems and flood control infrastructure. Now, let's talk about uniform and non-uniform flow. Uniform flow means that water moves with the same depth and velocity along the entire length of the channel. This typically occurs in man-made channels like concrete-lined canals where the slope and shape are consistent. It allows engineers to design predictable systems for irrigation or wastewater transport. Non-uniform flow, on the other hand, happens when depth or speed changes along the channel, often seen in natural rivers with rocks, curves, or variable slopes. Understanding this is important when designing bridges, culverts, or erosion control structures. Moving on to laminar and turbulent flow. Laminar flow is smooth and layered, where water particles move in parallel paths with little to no mixing. It's rare in large natural channels but can occur in laboratory flumes or very small-scale irrigation lines. Laminar flow is ideal for precision experiments and systems needing minimal disturbance. Turbulent flow is what we see most often in real life. Water swirls, forms eddies, and mixes as it moves, like a river during rainy season or water rushing over boulders. While turbulent, this flow enhances oxygen mixing in water, which supports aquatic ecosystems and helps distribute sediments naturally in rivers. In open channel flow, water can move at different speeds and depths depending on the slope, flow rate, and channel shape. One way to describe this is through flow regimes, subcritical, critical, and supercritical, and we use something called the Froude number to tell them apart. Let's start with subcritical flow. This is when the flow is slow and deep. The water moves gently, and gravity is the dominant force. It's like watching a calm river slowly drifting downstream. In subcritical flow, surface waves can move upstream, which means if you throw a pebble, the ripples might travel backward. Next is critical flow. This is the balance point between gravity and the force of the moving water. The water speed is exactly equal to the speed of wave movement. It's a very specific condition, like a fine line between slow and fast flow. Engineers often aim for this condition in designs like spillways and flumes because it's easy to measure and analyze. Finally, we have supercritical flow. This is when the flow is fast and shallow. The water moves with so much energy that it can't be influenced by disturbances upstream. Imagine water rushing down a steep slope or a fast-moving stream. It's quick, intense, and hard to control. Understanding these flow types is essential in hydraulic engineering because they affect how water behaves, how structures are built, and how we manage things like floods, irrigation, and erosion. Now let's look at the key components that make up an open channel system, each playing a vital role in how water flows. First, the channel bed. This is the bottom surface of the channel where the water flows. It can be made of soil, rock, concrete, or any material that forms the base of the channel. The roughness of the bed affects the flow resistance and speed of the water. Next is the flow depth. This refers to the vertical distance from the channel bed to the water surface. Flow depth influences both the velocity and volume of water, which is essential for designing structures like weirs and culverts. Then we have the free surface. This is the top of the water in an open channel, directly exposed to the atmosphere. Unlike closed pipe flow, the free surface is affected by wind, pressure, and slope, all of which impact how water moves. Channel slope is another important factor. This is the incline or gradient of the channel bed. A steeper slope means faster flow, while a flatter slope results in slower water movement. Engineers carefully design slopes to control velocity and prevent erosion. Finally, we have the hydraulic radius. This is a key geometric property, calculated as the cross-sectional area of flow divided by the wetted perimeter. It helps us understand the efficiency of flow. The higher the hydraulic radius, the more efficiently water moves through the channel. All these components work together to determine how water behaves in an open channel, from natural rivers to engineered irrigation systems. Flow parameters. In open channel hydraulics, we use several important parameters to describe how water moves. Understanding these flow parameters is key to analyzing, designing, and managing any water system, from irrigation canals to natural rivers. Let's go through each one. First, flow rate, symbolized as Q. This refers to the volume of water passing through a section of the channel per unit of time. It's usually measured in cubic meters per second. In simple terms, it tells us how much water the channel is carrying. For example, a large river might have a flow rate of 100 cubic meters per second during peak season. Second, velocity, represented as V. Velocity is the speed at which water moves through the channel, measured in meters per second. Faster velocity means water reaches its destination more quickly, but it can also increase erosion risks. That's why understanding velocity is crucial in designing safe and stable channels. Third, depth, represented by the symbol Y. This is the vertical distance from the water surface down to the bottom of the channel. The depth affects the pressure at the base of the flow and helps determine how much water the channel can safely carry without overflowing. Fourth, we have cross-sectional area, or A. This is the area through which water flows in the channel. It depends on the shape of the channel, whether it's rectangular, trapezoidal, or circular. A larger area generally means the channel can carry more water. Fifth, wetted perimeter, represented as P. This is the total length of the channel surface that touches the water, including the bottom and sides. A longer wetted perimeter creates more friction, which can slow the water down. And finally, hydraulic radius, or R. This is a measure of how efficiently water flows through the channel. It's calculated by dividing the area by the wetted perimeter. So, R equals A divided by P. A higher hydraulic radius means less friction, which results in smoother and faster flow. Together, these 6 parameters, flow rate, velocity, depth, area, wetted perimeter, and hydraulic radius, are the foundation for designing effective irrigation systems, flood control structures, and drainage networks. By understanding them, engineers can create channels that move water efficiently and safely. Manning's equation is a key formula used in open channel hydraulics. It helps us estimate the velocity of water flowing through a channel by considering 3 main factors: the roughness of the surface, the shape and size of the channel, and the slope or steepness of the bed. This equation is especially useful because it's simple, yet reliable for many real-life applications. Engineers use it when designing systems like irrigation canals to ensure crops get the right amount of water, drainage ditches to remove excess rainwater in farms or roads, floodways to safely direct water during heavy storms, urban stormwater drains to prevent city flooding. Whether it's a concrete-lined canal or a grassy roadside ditch, Manning's equation helps predict how fast water will move and how much will flow. Manning's equation for velocity is used to calculate how fast water is moving through an open channel. The formula is velocity equals 1 divided by n, multiplied by r to the 2/3 power, and multiplied again by s to the 1/2 power, where v stands for velocity, measured in meters per second. N is the Manning's roughness coefficient. It represents how rough the channel surface is. A concrete channel has a low N value, while a rocky stream has a higher one. R is the hydraulic radius, which is the area of flow divided by the wetted perimeter. It reflects how efficiently the water flows through the channel. S is the slope of the energy grade line. In most cases, it's the slope of the channel bed. This equation helps engineers understand how fast water will move in a given channel, which is crucial for preventing flooding and designing safe infrastructure. Now, to find flow rate, we simply take the velocity we just calculated and multiply it by the cross-sectional area of flow. The formula becomes Q equals V times A, where Q is the flow rate in cubic meters per second, V is velocity, as we've just discussed, and A is the cross-sectional area of the flow. For example, if velocity is 2 meters per second and the area is 3 square meters, the flow rate is 6 cubic meters per second. These formulas, Manning's equation and the flow rate equation, are essential tools for agricultural and biosystems engineers. They help us design canals, ditches, and floodways that are efficient, safe, and suited to their environment. The Froude number is a dimensionless value used to describe how fast water is moving compared to the force of gravity. It helps us understand the type of flow in open channels. Also, it is a key concept in open channel hydraulics. It compares the speed of the water to the speed of small surface waves. For example, in a stormwater channel, calculating FR can help decide if the design needs protective lining or energy-dissipating structures. That's why understanding the Froude number is essential for safe and effective water engineering. Mathematically, it's the flow velocity divided by the square root of gravitational acceleration times depth. When Froude number is less than 1, the flow is subcritical, meaning it's slow and controlled, common in rivers or large canals. When Froude number equals 1, the flow is critical, right at the balance between gravity and inertia. When Froude number is greater than 1, the flow is supercritical, which means water is moving fast, often shallow, and harder to control, like water in steep mountain streams or drainage chutes. Knowing the Froude number helps engineers design safer, more efficient water systems by predicting flow behavior. Next, we moved on to the flow measurements in open channel. Measuring flow in open channels is essential in water management, agriculture, and engineering. There are several methods, ranging from simple to advanced technologies. Float method, one of the easiest ways to estimate velocity. A floating object is placed in the water, and the time it takes to travel a certain distance is recorded. While simple, it's only accurate for surface flow and rough estimates. Current meter, this device has rotating blades and is placed in the water at different depths to measure velocity more accurately. It's commonly used in rivers and canals for more precise data. Weirs, these are overflow structures like V-notch or rectangular weirs, placed across the channel. The height of water flowing over them can be used to calculate flow using established equations. For more information about weirs, visit our YouTube channel as we have finished discussing this topic. Next, flumes, devices like the partial flume are installed in channels to guide water through a specific shape, making it easier to measure flow based on depth at a certain point. They are less likely to clog and are good for wastewater and irrigation. Acoustic Doppler devices, these use sound waves to measure how fast water is moving. They are very accurate and useful in large or deep channels, but they can be expensive and require technical knowledge. Another method is the use of pressure transducers. These devices use pressure sensors placed underwater to measure the depth of the flow. Since water pressure increases with depth, we can use the pressure reading to calculate how deep the water is, and from that, estimate the flow rate, especially when the channel geometry is known. Pressure transducers are often used in automated systems for continuous monitoring, such as remote stream gauges, where data is transmitted to water agencies in real time. They are efficient and reliable, especially for long-term observation in both natural and artificial channels. These tools help ensure that water is used efficiently, whether it's for irrigation, flood control, or monitoring rivers and drainage systems. Applications of open channel flow. Open channel flow plays a vital role in many civil, agricultural, and environmental systems. One major application is in irrigation, where water is transported through open canals and ditches to farms, helping grow crops efficiently. In drainage and flood control, open channels guide excess rainwater or surface runoff away from urban and agricultural areas, preventing flooding and erosion. Open channels are also used in hydroelectric power plants. Flowing water is directed through open conduits to spin turbines and generate clean energy. In wastewater management, open channels carry treated or untreated sewage between treatment facilities or into final discharge points like rivers. For navigation and transportation, rivers and man-made canals provide pathways for boats and barges, supporting trade and travel. Lastly, open channels are monitored in environmental conservation, helping scientists and engineers understand how streams and rivers behave under natural and changing conditions. These applications highlight just how important open channel flow is in both natural systems and man-made infrastructure. In summary, open channel flow refers to the movement of water with a free surface, something we commonly observe in rivers, canals, and ditches. These channels can either be natural, like streams and creeks, or artificial, such as irrigation canals and drainage ditches, each serving essential roles in water transport and management. We explored different types of flow, including steady or unsteady, uniform or non-uniform, and laminar versus turbulent, each describing how water behaves under different conditions. We also discussed flow regimes, subcritical, critical, and supercritical, classified using the Froude number, which compares flow velocity to wave speed. Understanding flow parameters like velocity, depth, and hydraulic radius helps engineers analyze and design open channels. Tools like Manning's equation allow us to predict flow velocity based on physical channel properties. To measure flow, a variety of methods are used, from simple ones like the float method to advanced technologies like acoustic Doppler devices and pressure transducers. Each method serves different levels of accuracy and field conditions. Finally, we saw that open channel flow is critical in many real-world applications, from irrigating crops and controlling floods, to generating power, treating wastewater, supporting navigation, and preserving natural water systems. Understanding open channel flow is not just about theory, it's about solving real problems and managing water responsibly in both rural and urban environments. For the assessment, we've prepared a separate video to test your understanding of Introduction to Open Channels. Check it out on our channel to assess your knowledge and reinforce what you've learned. It's a great way to boost retention and prepare for real-world applications or exams. And that wraps up our journey through open channel flow. I hope you learned something valuable today, whether it's about the basics, the types of flow, flow measurements, or the important role we engineers play in managing our water systems. Reminder: let's clear up a common misconception. Agricultural and biosystems engineers don't just deal with farming. Sadly, many still overlook or misunderstand this profession, often leading to unfair stereotypes. But here's the truth: ABE graduates are jack of all trades. We are equipped with a wide range of skills and knowledge that go far beyond agriculture, from designing irrigation systems and flood control structures to managing watersheds and developing sustainable technologies. Open channel flow is just one example of where our expertise shines. Whether it's in irrigation, drainage, or environmental protection, our work helps ensure water is used wisely and safely. So, to every aspiring ABE student or young engineer out there, be proud of your path. Your knowledge matters. Your work impacts lives. Keep pushing forward, because you are building a future where engineering meets sustainability, and that's something the world truly needs. If you found this video helpful, don't forget to like, subscribe, and share it with your fellow learners and future engineers. This is AB Engineering Guild, where we learn, apply, and transform. See you in the next video, and keep engineering a better world.